In our last video, we went through various transformations of functions. In fact, we covered three of the big four, as I would call them. So one we did is horizontal translations. In other words, when a function or a graph moves to the left or right. And we also talked about vertical translations. In other words, when a graph or a function is moved up and down. And then we also looked at vertical stretches or compressions and reflections. So that's three of the four. Today, we're going to cover the last one, which is the horizontal stretches, compressions, and reflections. So this one is brand new. You never did this in grade 10. We never applied this to a quadratic, but in this lesson, we're going to see how it could apply to various functions in general. But before we get there, let's just do a little review. So let's have a warm-up in terms of graphing some various transformations of functions. So for each function g of x, we want to identify the base function and describe the transformation in both words and in the form g of x is equal to a times f of x minus d plus c, so in function notation. We also want to graph g of x and state the domain and range of g of x. So lots of things to do, but let's go off and do this. So it's a pretty good review. So for a, we have g of x is equal to negative 4 root x. So the parent function here is the square root function, so root x. So let's describe the transformation in words. So again, my hint in not going off and doing this is getting my A, C, and D attributes. So in this case, we just have an A attribute. In other words, it's only a value that's being multiplied to my function, or that's outside my function. In this case, that A value is actually negative 4. So this implies that this is going to be a vertical stretch by a factor of 4. And it's also vertically reflected since A is negative. Okay, so one of the things I just want to highlight is that this is stretched, even though A is less than 1, because when it's talk about A being greater than 1, then it's vertically stretched, then it's stretched. But here we actually want to look at the absolute value of A, and that tells if it is stretched or compressed. So the absolute value of negative 4 is actually 4, so this is just stretched. So the negative just tells us it's going to be reflected, but it's going to be reflected but also stretched at the same time. If the absolute value of A in this case is between 0 and 1, then it's going to be compressed. So we want to rewrite this function now in function notation. So here we have g of x is, so we always say our A value, which is negative 4. Then we have our actual function, and inside our function is just x. So that's that. So notice that in this this g of x, this transformation, there is no vertical or horizontal translations. In other words, there's no c or d values. So let's go off and graph this. Since there is no translations, in other words, c and d is 0, we could just use g of x directly. And our key points on our x value, for the x value for a reciprocal, sorry, a radical function, a root function, is going to be 0, 1, 4, and maybe we'll add in 9. So here we're going to say what's g of x. So it's going to be f of x, which is the square root of 0 times negative 4, so that's going to be 0. F of 1 is going to be square root of 1, which is 1 times negative 4, so that's going to be negative 4. F of 4, which is the square root of 4, that's going to be 2 times negative 4, that's going to be negative 8. And then finally, f of 9, which is the square root of 9, which is 3 times 4 is going to be negative 12. All right, so let's go off and label our axes and put in our scale. And let's see what this graph looks like. So here we're going to get 0, 0. So let me just do this in red. 0, 0. We got 1, negative 4. So it's going to be coming down over here. 4, negative 8. So 1, 2, 3, 4, and negative 8. It'll be somewhere down here. And then the last point is 9, 12. And that might be, it's off our grid a little bit, but that might be right over there. I'm just eyeballing it. So again, this is the shape of the shooting arrow, but we recognize in this case it's going to be stretched by a factor of 4. So it's going to look like it's really pulled down because it's also reflected. So we're going to connect the dots in a nice smooth curve. That's going to look like a shooting arrow like that. So this is g of x. Okay. So the next one is a little bit more tricky. We have the reciprocal function. So let's go off and identify the parent function. I already said it's the reciprocal. So f of x here is 1 over x. So that's my parent function. And let's just rewrite this in function notation first. So here's going to be g of x is equal to f of. So here the tricky part here is that since x plus 3, again, that's reciprocal is in the denominator, so that is our function. So that's going to be inside x plus 3, and we just have a minus 1 on the outside. So here we just have a pure translation. There's just no vertical stretch or reflection on this. So we're going to see that because here my a value is actually on top, and that's just 1. My c value, in other words, what am I adding on the outside, is going to be negative 1. And my d value, again, we want to focus on this, and it's going to be what makes that 0. So let's write this out. My a value is just 1, so really there is no stretch or compression or reflection. We don't have to say anything. My c value is negative 1, and my d value, again, what makes that 0, that's going to be a negative 3. So we want to graph this. So one thing to remember for the reciprocal function, there is let's write out the transformations. Didn't write out the transformations. So this is just 2 shifts. So this is shifted down 1 unit. So c is negative, and to the left, and it's left because d is negative, so to the left 3 units. So just to kind of highlight again, our basic reciprocal function is going to look like this, where our asymptotes are actually on our x and y axes. Okay, so again, because this is a translation, it's moved up and down, our asymptotes are going to move as well. So let me just kind of draw the asymptotes here in green. So here, because it's moved down by 1, so our horizontal asymptote now becomes down here at x equals minus 1. And because it's moved to the left 3, our vertical asymptote is right there at x equals, the horizontal asymptote is y is equal to negative 1. And the vertical asymptote is x is equal to minus 3. So how do we get some of the key points on our graph? So let me just kind of do this down here, x and y. So in our parent function, one of the key points that we're looking at is 1, 1. In other words, when a denominator is 1, the reciprocal of 1 is just 1. So that's one of the key points we sort of want to map across in our transformation. So how do I get the denominator to be 1 in this case? So we were looking at x plus 3 is equal to 1. So really x is going to be negative 2. So we're going to start at negative 2. And then we're also going to go, in this case, to the right, incrementing by 1. So that's going to be negative 1. And we'll go to the left, in other words, in this case, towards the asymptote of x equals minus 3. We'll go by half. So that's going to be negative 2.5. So let's do the transformation of this. So negative 2 is just going to be 1, right? Negative 2 plus 3 is going to be 1, so it's just going to be 1 over 1. 1, so that's going to be 0. For negative 1, So again, our function is x plus 3. So there's going to be negative 1 plus 3. So that's going to be a half. Minus 1. So that's going to be negative a half. And then negative 2 and a half. So plugging that into g of x, that's going to be negative 2 and a half plus 3. So that's going to give me a positive a half. So reciprocate positive a half is going to be 2. 2 minus 1 is just going to be 1. So let's go off and plot those 3 points right now. So we get negative 2 comma 0. So oops, I didn't label our axes, and let's put on the scale here. So 2, 4, 6, 2, 4, 6. So let's zoom in here and let's plot our points. Negative 2 comma 0. So negative 2 comma 0 will be right there. And then we're going to have negative 2 and a half comma 1. So we get closer to our vertical asymptote. Negative 2 and a half and 1. So that'll be right there. And then negative 1 comma negative a half. So here we get negative 1, negative a half. So get closer to negative 1 to horizontal asymptote, but not there. So that looks kind of correct. So we're just going to connect the dots of our smooth curve and getting closer and closer to our asymptotes, but not touching it. So let's look at the other side, or the other part of the graph. And in this case, we want this point over here where we had negative 1 comma negative 1. In other words, we want our denominator to be negative 1. So in this case, when we have x plus 3, we want that to be negative 1. So in this case, that's going to be x is equal to minus 4. So that's where we're going to start off here is negative 4. And then again, we'll go to the left. In other words, when we get more negative, we want to decrement by 1 or go down by 1. So it's negative 5. And when we go to the other way, when we go to the positive direction, we actually just want to go down by a fraction. So in this case, I always choose a half. So it'll be negative 3 and a half. So let's do g of negative 4. So that's going to be negative 4 plus 3, which is a negative 1. Reciprocal of negative 1 is just negative 1. And we're going to subtract 1. So that gives us negative 2. When we do g of negative 5, so that's going to be negative 5 plus 3. So that's going to be negative 2. So we get a negative a half minus 1. So negative a half minus 1. That's going to be minus 1 and 1/2. And then looking at negative 3 and a half. So negative 3 and a half plus 3. That's going to give me a negative a half. We reciprocate negative a half. That's going to be minus 2. So minus 2 minus 1 is going to be negative 3. So we have these 3 other points. And let's go off and put that in. So here we got negative 4 and negative 2. So 1, 2, 3, 4, and negative 2. So that's looking pretty good. I'm just going to move my y asymptote here. So my vertical asymptote just to be directly on. Oops. Let me try to select it. And it's not picking it up. Let's try this. No, that's picking up. So we'll just leave it. I'm having a hard time trying to move it, but here we're going to get negative 4, negative 2, so that's going to be right there. So it looks like it's really close to the asymptote, but only because I sort of missed the line by a little bit. The next point we'll want to plot is negative 5, negative 1 and 1/2. So negative 5, negative 1, 1/2 would be right there. And then negative 3 and a half and negative 3. And that's going to be negative 3 and a half and negative 3 will be somewhere down here. Okay. So let's connect that with a nice smooth curve. And getting closer and closer asymptote, but not touching it. All right, so that's what that graph looks like. I know it's having some issues with the screen here. Can't quite see the numbers on the right, so there it is. So that's how we graph that. So let's go on to today's concept of horizontal stretch, compressions, and reflections. So really, one success criteria that we're looking at, we're really just focusing on the one transformation here. And really what we're going to understand is what are the effects when we multiply x by a certain number within our function now. So remember a was multiplying a function outside of a function. In other words, we take the value of a function, whatever that answer is, and multiply by a. So this one's going to be very different because now we're going to multiply x by a number and then apply that to the function. Okay, so we already did something inside a function already when we add or subtracted something to x that was inside a function. Realize that moved it horizontally, so to the left or right. So we're going to find out what the effects is when we actually multiply a number by x. So multiply x by a number. So we're going to look at the square root function. So the parent function here is going to be f of x is equal to root x. And I've kind of filled in the table of values for us already and what the parent function looks like. So 0, 0, 1, 1, 4, 2, 9, 3, 16, 4. So I'm just going to graph this. And maybe I'll just graph this in black. So let's label our axes, give us a scale. And we're going to look at our parent function so that we could kind of compare and see what's happening with the other functions relative to this. So we got 0, 0, 1, 1, 4, 2, and then 9, 3. We'll put us right there. So there is our parent function f of x. Okay, so when we're going to investigate, a function, a transformation like root 2 of x, we're going to take a different approach. And hopefully by taking this approach, you can kind of see what the pattern is with x and this number, in this case 2, being multiplied to x and what it kind of looks like. So here we want the same answers, 0, 1, 2, 3, 4, as our parent function. So in this case, what's going to be the square root of x? So what do we need the square root of to get 0? Well, it's just going to be 0. So this one isn't straightforward because we're just dealing with 0. But the next one is that we want the square root of 1. So here we want the square root of 1. But really, this is 1 is equal to 2x. Because really, with 2x, when we want 2x, we want the value to be resolved to 1, so that we square root of 1, and that's going to be 1. So here, recognize that x has to be 1/2. So really, we get the point 1/2, 1 in g of x. And that kind of makes sense if we think about it. Well, if x is 1/2, what's 1/2 times 2? Well, that's going to be a 1, and square root of 1 is going to be a 1. So likewise, when we want the answer 2, when we want the square root to be the answer 2, we know that we need to square root 4. But in this case, 4 has to equal 2x. So what's x going to be? So here we need to divide by 2. So x actually has to be 2. So we're going to get a point 2, 2 here. And I'll just write over here, we're going to get a point 1/2, 1. And over here we get 0, 0. All right, so following this pattern, what do we need to square root to get 3? Well, that's going to be 9. So we want the square root of 9. That's going to give us 3. But in this case, we need that's going to be equal to 2x, because that's what we're square rooting is 2x. So x is actually going to be, in this case, 9 over 2. So here we have another point, 3, in this case, 9 over 2 is 4.5. And the last example here, I should give us more space here, but hopefully we kind of see what's going on, is that in order to get the answer 4, we need to square root 16. But in this case, what we're square rooting is 2x, so that implies that x must be 8. So here we're going to get the point 4, 8. So really, can you kind of see that in order to get that value, what we want is we need to take x and really divide it by 2. And whatever we want, we need to divide by 2. And because we happen to be multiplying by x by 2. So we need to sort of do the opposite. So let's go off and graph this. So this one's in blue. So we got 0, 0. Then we got 1/2, 1. So 1/2, 1 would be right there. Then we're going to get 2, 2. So 2, 2 right there. And then 3, 4.5. So 3, 4.5 would be right there. Sorry, I mixed that around. That's 4.5, 3. I know it's looking kind of weird. So that's 4.5, 3. And I recognize I did the same thing with this one down here. So that's really the 0.8, 4. So here we want 4.5, 3. So 4.5, 3 would be like right there. And then the last point we have here is 8, 4. So 8, 4 would be right here. So again, we could connect this. A nice smooth arrow. We know it's going to get flatter and flatter and flatter. Okay. So what we kind of see here is this is actually compressed. Now it looks like it's hard to tell it's compressed. But again, we're going to look at how many points do we actually label here. Here we actually label 1, 2, 3, 4, 5. Compared to original function, or our parent function, we only label 4. So really kind of compressed everything in. We pushed it in. Another way we could kind of see this as well is that if we take this point over here, let's do over here, we really moved it in to over there. Because in order to get that same answer of 9, originally, sorry, the same answer is 3, originally was 9, but now we actually have 4.5. So this has the effect of really kind of compressing our graph. So this blue line here is g of x. So let's look likewise with h of x. So I'm going to do this in red. So again, we want our answers to be 0, 1, 2, 3, 4. So in order to get an answer of 0, we must square root 0. In this case, it's just going to be 0. It doesn't because we multiplied that half, it's still going to be 0. The next one's going to be more tricky because in order to get an answer of 1, in other words, that's square root, the answer be 1, we need to square root 1. But 1 in this case is equal to a half x because we're square rooting a half x, but we want that answer to be 1 so that we could square root 1 to get the answer 1. Okay, so here x is actually going to be 2. So we actually have a point 2, 1 here. So this point is 0, 0 still exists. Likewise, if we keep following this pattern, is that in order to get the answer of a square root to be 2, we need to square root 4. But what we're square rooting is 1/2 x. So 1/2 x must equal to 4, so that means that x must equal 8. So here we're going to have a point 8, 2. And then likewise, we're going to keep coming down. We need to square root a number to get 3, and that number must be 9. So we must square root 9 in order to get 3. But then 9 is equal to 1/2 x because that's what we're actually square rooting in our function. So that implies that x is going to be 18. So here we're going to have a point 18, 3. And then the last one is square root of 4. To get an answer 4, we must square root 16. So in this case, 16 is 1/2 x. So that implies that x is equal to 32. So we're going to have a point 32, 4. So we can kind of see ahead that we actually can't graph a lot of these points because the x is so big. In fact, we could only graph 3 of them. 0, 0, 2, 1, 8, 2. So let's graph those. So we still have 0, 0 right here. 2, 1. So 2, 1 will be right there. And then 8, 2 will be right here. And that's all we can do. But we know that this graph is smooth and it's going to come down to this way. Okay. So one of the effects that we can kind of see is that this is actually horizontally stretched. Really, we took this main point over here, so this one over here, and we moved it, or it's become all the way to the right. So it's almost we took it and yanked it to the right. So we're horizontally stretching this. So what we're seeing is the net effect of that when it's a half, it's actually being stretched. When it was 2, it's being compressed. So this is almost like the opposite of what's happening with the A value. Because when we said the A value, when the A value is greater than 1, it was actually being stretched. And when A value is between 0 and 1, it is actually being compressed. So the opposite is happening here with the horizontal stretch and compression. Lastly, just to kind of highlight what's happening when it's negative, we could almost kind of guess what might be happening here. So we'll do this in purple. So in order to get the answer 0, we must square root 0. Now, in order to get the answer 1, we must square root 1. But in this case, we're square rooting negative x. So 1 must equal to negative x. So that implies that x is equal to negative 1. So we're going to have a point negative 1 comma 1. In order to get the answer 2, the square root to be an answer of 2, we must square root 4. But in this case, again, what we're actually square rooting is negative x. So that means negative x must equal to 4. So that implies that x is equal to negative 4. So we have in the point negative 4 comma 2. Again, continuing that pattern, in order to get the answer 3, we must square root 9. But 9 is actually going to be equal to negative x. So that implies that x is equal to negative 9. So we have a point negative 9 comma 3. And finally, the last one, in order to get the answer of a square root to be 4, we must square root 16. So 16 in this case is going to be equal to negative x. So that implies that x is equal to minus 16. So we have a point negative 16 comma 4. So let's plot that. So we still have 0 comma 0. But in this case, we got negative 1 comma 1. Negative 4 comma 2. So 2, 4, negative 4 comma 2. And finally, negative 9 comma 3. So what we're going to see is that this is really a true reflection of f of x. So this was n of x, but in this case it's reflected horizontally, right? So really what we're saying is all the x's, because they were positive, we have a negative in front of that, they all become negative now. So this is why we have a horizontal reflection with that. Okay, so hopefully this was a good enough example to sort of highlight what's happening when we multiply a number to x. We're actually going to get a horizontal stretch or compression. And if the number that we're multiplying to x is also negative, then we're also getting a horizontal reflection as well. So let's summarize. So given any parent function f of x and a function g, and I should actually write this, it's not actually written properly. This is where g of x is equal to f times k of x. In other words, we're multiplying something to x inside our function. Then it has a transformation of x that has the following characteristics. That if k is less than 0, that is k is negative, then the graph is reflected in the y-axis. In other words, it's as if the mirror is sitting on the y-axis. And we could also call it, if you want, a horizontal reflection as well. Here's the tricky part, is now if the absolute value of k is greater than 1, the graph is actually horizontally compressed. And the factor that we say is compressed by is actually 1 over k. And in this case, really the absolute value of 1 over k. So in this case, what we're seeing here is when k was 2, this was actually compressed by a half. Okay? Lastly, if the absolute value of k is less than 1, then the graph is actually horizontally stretched and the factor is still 1 over k. And what a little bit of numeracy here is, one thing we're going to recognize that regardless if it's horizontal or vertical compression, the factor is always going to be less than 1. And here's the one way to sort of resolve this when it's horizontal is if k is greater than 1, when we reciprocate that, and that's what 1 over k is, that number is now going to be less than 1. So for example, if k is 2, reciprocate that, that's going to be 1 over 2. Even if it's a fraction, k is 3 over 2. We reciprocate that, that's going to be 2/3, so it's automatically going to be less than 1 in this case. So we recognize that the horizontal compressions, the factor is always going to be less than 1. Likely, conversely, when we have a horizontal stretch or any type of stretch, the factor is always going to be greater than 1. So that kind of makes sense. Less than 1, we're making it smaller, so compressing. Greater than 1, we're making it bigger, so we're actually stretching it. So likewise, the bit of numeracy, if our value is less than 1 and then we reciprocate that, so that's what 1 OK is, we're always going to get a number that's bigger than 1. So one of the tips or tricks we'll go off and sort of do horizontal transformations in terms of stretches and compressions is that if a point x comma y is on f of x, whatever function we're transforming, then it's transformed to the point x over k. So we take our original value of x on my parent function, or f of x, and we divide by k, and that gives us the new x value for a transformed function. So I'm going to fix this over here. So that's not correct. This is really what g of x is equal to f times k of x. Okay, so let's look at an example. So if f of x, if my parent function here is 1 over x, and we're transforming it by really multiplying by a third to x inside our function, what is this going to look like? So first, let's graph our parent function f of x. So we know that we're going to have asymptotes, both horizontal and vertical. And since we're not moving this graph, not moving this graph, but since g of x has no horizontal or vertical translations and there's not being shifted at all, the asymptote is going to stay as well. So here we're going to get x is equal to 0. So that's the vertical asymptote. And the horizontal asymptote is y is equal to 0. So let's look at our parent function. So we'll do this in blue maybe. So we recognize, we hopefully remember graphing this so many times that we got 1 comma 1. Then we're going to have a half comma 2. And then a half comma, and then a half comma 2. I meant 2 comma a half for this one. So let's connect the dots. And so that's what our parent looks like. Okay, and I'm actually going to write down those points, x and y. So we had a half and 2, 1 and 1, 2 and a half. Then graphing on the other side, we get -1, -2, and -1/2. And that's going to become, our y value is going to be -1. Well, -1/2 reciprocated is going to be -2. And -2 reciprocated is going to be -1/2. So let's go off and plot that. I forgot the arrow there. -1, -1, -1/2, and -2. So that's down here. And then -2, -1/2 is over here. So I forgot to put a scale on here. So it's all by ones again. 2, 4, 6. 2, 4, 6. So we're going to connect the curve this way. Okay. So our trick, again, is the transform points. So when we're looking at g of x now, so I should maybe not have written y. Maybe a better way to describe this is what we're actually calculating for is actually f of x. And now we want to look at g of x. And then appropriate x values. So what we're going to say here is actually we're going to have the same answers, 2, 1 and a half, right? Because y is just going to be transformed to y. There's no changes in y. In this case, there's nothing being multiplied to the function outside of function. So that's why y just stays as is. There's nothing added to it after a function. So y is not transformed at all. But we'll have to look at the x. So here we need to take original x value and divide by k. So what's my k value in this is actually 1/3, right? Because it's 1/3 being multiplied to x. So when we divide by k, we're dividing by a third. So really this is the same thing as multiplying by 3. So we're taking each of these values and we're multiplying by 3 now. So 1/2 times 3 is 3/2. 1 times 3 is 3. 2 times 3 is 6. So we have these new set of 3 points for g of x, negative 3, comma 2, 3, comma 1, 6 and 1/2. So let's plot that. So 3, comma 1 would be right here. So in other words, this point has transformed to that point over there because we sort of multiply it by 3. Likewise, we're going to have 6.5. So 6 and 1/2 would be over here. And then we have 1 and 1/2, comma 2. So 1 and 1/2, comma 2 will be right there. So because it has the same asymptotes, we're going to start to draw the lines. So it's going to get closer and closer to it, but not touch it. Okay, so we can kind of see over here, there's a little bit more space between our curve and our asymptote. Only because it's almost like, again, we're pulling it to the right. We're stretching it to the right. So that's why it's kind of yanked that way. Well, conversely, on the left, we're actually pulling it to the left. So either way, we're stretching it. We're pulling it away from the asymptotes in this case. So here we're going to take each of my x values and do the same thing, multiply by 3. So that's going to be negative 3 over 2. That's going to be negative 3, and that's going to be negative 6. So my new points here are going to be negative 6, comma negative 1/2. So 2, 4, 6 and 1/2 will be right there. Negative 3, negative 1 will be right there. And then negative 6 and sorry, we did that. Negative 3, negative 1 and 1/2 and negative 2. So negative 1 and 1/2 and negative 2 would be over here. So again, we can connect that with a smooth curve with the ends getting closer and closer to our asymptotes, but not touching it. So this does look like it does have effect that it is being stretched. In this case, it's being stretched by a factor of 3. All right, so this is how we would graph something when it only strictly has a horizontal stretch or compression and possible reflection. In other words, our transformation is only a k in there, and we're only multiplying something to x. So for homework, it's a little bit smaller. It's only just to try to get really practice idea because it's totally brand new. So here's the homework, and also graph these 2 questions as well.